I start off with, we're going to just look at different strategies to use when we're attempting integration. And, well, the first one is obvious. Look for an obvious solution. So I guess what I'm talking about is the ones where in extension 1 they might give us a substitution to use and we go, oh geez, what'd you do that for? Surely I can just write it this way. So when you see it, it's obvious. So you try and just find some function in the integrand whose derivative also occurs. So something like this. Let's say in extension 1 they'd probably do something like, oh, well, let u equal 1 minus x squared or something like that. But if you look at it and you say, oh, hang on, I can create the derivative on top here and make it derivative times the function to some power and save myself some time. So I know that's going to be minus a half, the integral of minus 2x on root 1 minus x squared. So I have the situation of du on root u, and so as I've mentioned before, du on root u, 2 root u, not on the reference sheet, certainly worth remembering to save yourself some time. So a half times 2 becomes 1, so we get the negative root u in this case 1 minus x squared, plus a constant. Sometimes, and this was the idea of integration by substitution, is when we manipulate it into one of the standard forms that we know. Here's a very interesting one. E to the x plus e to the x, as in the power is x plus e to the x. So how do you manipulate this one? Well, you use your index laws. If I rewrite that, I can rewrite it as e to the x times e to the x. And I now have derivative times the exponential to a function. So therefore, it's e to the function, e to the x, plus a constant. So we want to manipulate this into a standard form. What we got? Well, the main thing I'm seeing there is e to the x on the bottom and e to the x on 2 on the top. I know when I differentiate exponentials, the power stays the same. So some sort of manipulation. Okay, an inverse tan one, that would make sense, because now the e to the x on the bottom would be the square of the e to the x on 2. So let's try and get it there. And there it is. On the bottom, I want a squared plus function x squared. Now I've factorised out the 3 on the bottom. So that way my function is just e to the x. So on the bottom I get 2 plus e to the x on 2 squared. And on the top, I want the derivative of the e to the x on 2, so I make that a half e to the x on 2, means I now need 4 out the front, but now I've got it in that form. So inverse tan, but remember inverse tan is 1 on a out the front, so I get 4/3, 1 on a, which in this case is the square root of 2, 1 on root 2, the inverse tan of e to the x on 2 on root 2, well, let's just tidy up that fraction out the front, so 2 root 2 on 3, inverse tan, e to the x on 2 over root 2 plus a constant, of course. Simplify the integrand if possible. Algebraic manipulation, trig identities, those sorts of things come in handy. So you see something like this. Tan theta on sec squared. Shame it wasn't the other way around. I mean, if it was sec squared on tan, we'd be okay, because sec squared is the derivative of tan. But unfortunately, it's in the denominator. So we need to manipulate this. So I'll turn everything into sine on causes. If I'm unsure what to do, change everything into sine on causes. Let's see what happens. So it's now sine on cos, and sec squared becomes 1 on cos squared, so invert and multiply. I now have sine cos. Oh, okay, now that's something nice. So we've got a half of sine 2 theta, and so we know that'll be minus a quarter cos 2 theta, plus a constant. Something like this is not immediately obvious. X cubed root 4 minus x squared. There's the hint on the right there. Factorise by using the expression in the grouping symbols. Well, in the grouping symbols this time is the square root sign, so 4 minus x squared. A multiple of its derivative or a combination of both. Bingo. That's how I'm going to rewrite it. So a multiple of its derivative or a combination of both. So the function was 4 minus x squared. I got an x cubed out the front. So a multiple of its derivative. The derivative is just x. I'm going to multiply it by the actual function itself. That'll get me the x cubed. But I've got to balance it out. So I've got the minus x, 4 minus x squared. To balance that out, I need a plus 4x. What that now allows me to do is to rewrite the two different expressions now, but both of them are 4 minus x to some power, and both of them I have x out the front, so I can create the derivative. So that's what we call algebraic manipulation. So now I can just integrate. Of course, minus x on the first one is not the derivative. It should have been minus 2x. So I've got a half of add 1 to the power over the power. And the second one, 4x, again, it should have been minus 2x. So I've got minus 2 times 2/3 4 minus x squared, 3 on 2. And there's our answer. I suppose I could have factorised that, couldn't I? But oh well. Classify the integrand according to its form. So in other words, what it looks like gives you a clue on how to approach the question. Rational functions, polynomial division, and then we'll go and use partial fractions. So some of these techniques are ones we'll look at later on. So partial fractions being one of those. Trig functions. Well, the power of the trig function will tell you which technique to use, and we'll spend some time looking at trig integrals. If there's a mixture of different function types, you might have an exponential with a trig function, then you're probably going to use integration by parts. Essentially, there really is only two ideas: substitution and integration by parts. Pretty much everything is one of those two ideas. All right, we shall begin with 4a and 4b.